Thank you, John. Can you hear me?
Yeah, sounds great.
Great. Thanks for organizers for giving me this opportunity to share some of our recent work on developing physical models to understand how the scaling exists and how we can potentially develop some strategies to go beyond the linear scalings. In this approach, we are going to use the Bayesian inference to learn some the model parameters. So just some simple background for people that came in. So in heterogeneous catalysis, of course, we care about what's happening on the surfaces. If you zoom into the catalytic interface, there are a lot of elemental steps could occur. For the reactants, they have to absorb on the surface and possibly dissociate and activity and diffuse to the active sites and form some new chemical bond to dissolve into the gas or solution phase. So I want to emphasize how strong, how stable the intermediates on the surface is really a critical indicator if the catalyst is working or not, even without looking at some kinetic barriers, simply because absorption energies are intrinsically correlated with the activation barriers through the BP correlations. So, so these are very general slides, very general phenomenon observing heterogeneous catalysis on metal surfaces. So simply they see that for the absorption energies of the common intermediates, if they are bonding through the same item, most likely they are linearly correlated. So they show that on a few different transition metal surfaces, even with different atomic structures of the active sites. So this phenomenon we see on not only carbon, nitrogen, and some other oxygen bonded species, and even some others. So interestingly enough, so the correlation, the linear coefficient is dependent how many unsaturated electrons or bond that you can form with, for example, hydrogen. You can see here for oxygen and OH. So they roughly have half scaling coefficient there because oxygen they can have two valence electrons can form chemical bond, and OH have one. So from some simple understanding, we can know why they have a linear correlation. But what's one of the important consequences of this type of linear correlation is the Sabatier principle. So basically, the optimum catalyst is some sort of in the middle of the molecule surface interaction energies. You don't want to the adsorbate bond too strong, that will limited by desorption of the product. If you don't want to bond too weak, then they have a hard time to activate a strong chemical bond. So you want something in between. So it's basically how strong this molecule or adsorbate interact with the surface is really the critical factor to control the catalytic processes. And if we can understand the fundamentals of the chemical bonding, hopefully we can understand the fundamental limits of the linear correlations and figure out the physical way to go beyond it. So that's the main scheme of my work here. So just one example for this linear correlation, I'm interested in the fuel cell catalysis. So for this reaction, you have to transfer for proton electron to the O2 to form water. So on the right, it shows basically the measured oxygen reduction activity from model surfaces as a function of OH binding energies. You probably see something like this type of volcano curve before. So basically the microcatalytic model, the dashed line showing here, and also the measurement, they see something interesting that basically the OH is a very good descriptor. You can compare to pure platinum, if you can weaken the OH binding energies, and then you can have a better performance. But there are limits. If you go too weak to the OH binding to the platinum or the active sites, then they become limited by the first step to protonate the O2. So this linear correlation is really the problem. Ideal case, if you show here, if you see here the free formation energy linear correlation OH with the OH and atomic absorbed oxygen here. In the ideal case, your OH free formation energy is about 1.23 electron volts. So you can operate at, so the last step of OH desorption can be operated as the equilibrium potential. But for this ideal scenario, you have to stabilize the OOH by a few amount, by a significant amount compared to the scaling line determines. So that's really the challenge. So how can we, is it really possible to break scaling between this OH and the OOH? So in order to answer the question, we have to look at it, the chemisorption model. So of course, the state-of-art chemisorption model is the D-band model. I'm showing some schematic here on the left. If you have some valence state interacting with the metal surfaces, and the metal surfaces are characterized by some delocalized S states and some narrow distributed D states. So first step, the interaction of the adsorbate with the broad SP state can form some resonance states. And following that, they can interact with the narrow D states, forming these bonding and antibonding states. And occupancy of these antibonding states really determines how strong this chemical bond is. If you have some metal surfaces that have a lower D-band center, then you can imagine the antibonding state will become lower in energy, get more populated, so you can have a weaker chemical bond. So on the right, it shows some experimental evidence about this theory really validate what you see on the left. And another evidence to show you briefly, this is you can think about this is the hydrogen absorption energy versus the D-band center of active sites. So on a range of model surfaces of the palladium on different type of substrate, you can see D-band center is really linearly correlated with the hydrogen binding energy very well. But this is only so D-band model can give you a really nice qualitative understanding about the chemical bonding. But in order to understand the fundamental limits of scaling correlations and how to go beyond that, we would like to go a little bit deeper and more quantitative understanding about chemical bonding. So then we have to go back to our the initial Newns-Anderson model that can give you a more quantitative understanding about chemical bonding. So this is a picture, you see it already. So basically, Newns-Anderson model can help us to understand how this, for example, this adsorbed resonance state, adsorbed energy level interact with the metal surfaces, forming this bonding state and antibonding states, and what's the formula to evaluate the binding energy of this type of interactions. So this is some sort of a parameter we have to introduce, but I don't want to bother you with too much details. So basically, the Hamiltonian on the top includes some one-dimensional energy contribution from the adsorbates, from the substrate, and the coupling between those two set of states. And you can, if you know some parameters in the Hamiltonian, you can solve it within some bilateral approximation using Green function approach. There are two information you can get out of it. One is density states projected onto your adsorbate valence orbitals. I can have this formula here. Another information that you can derive is how strong this adsorbate bond to the surface, which could include the SP band contribution and also D band contribution. And SP band contribution, typically in the model, will assume to be a constant value on the transition metal surfaces. And for the D band contribution, we can separate in two different parts. One is the one electron energy contribution that I can just simply integrate into the states. Another is the repulsion energy contribution that is really proportional to how large overlap of the two set of states is. So in this simple model, there is a few different parameters I want to briefly touch upon about it. One is basically this where is the adsorbate energy level is. So you can imagine you have a few frontier orbital adsorbates, and what's the energy level relative to the work function or firm level of your substrate. Another is how strong the coupling is, this VAK. So that's really determine the energy change of the interatomic coupling. And I should point out that the relative value are really tabulated on the book. And the last parameter is the overlap between the adsorbate states and the metal states. So that kind of influence orbital orthogonalization energies when they come together to interact. And for the metal states, we simply use the DFT calculated projected states onto the metal D states. So for these fault parameters, you can use more deterministic fitting to get those parameters with some training data. But I would like to take a Bayesian approach. So in this approach, so basically you can see this is the Bayes theorism. So basically what you want to figure out is what's the probability distribution of those parameters for given evidence or given data sets. And for our chemisorption models, the observation is DFT calculated absorption energies and the density states. So the important advantage of Bayesian approach is you can incorporate the prior knowledge if you have for each parameters, and this is basically the likelihood of observation for given parameter site, and the PE is normalizing constant in the Bayesian optimization. So this constant is really difficult to calculate directly. So you can use macro chain color sampling approach to sample the particle distribution without considering this normalizing constant, simply because in the Markov chain hopping, the probability of each step is only determined by the relative probability, not the absolute values. So this approach, you have less prone to trapping at the local minimum. So we use this the Bayesian optimization in PyMC with about 100K training steps for oxygen on pure metal surfaces. We have about 9 transition metal surfaces. So this is a learning result. So by training those density states and absorption energy of oxygen on those pure metal surfaces, we can derive the posterior distribution for those 4 parameters listed here. So they all have a very nice Gaussian distribution with some uncertainty on each parameter. And some parameters there's some correlations between them, but most of them are independent samplings. So one of the advantage of the Bayesian optimization is that you can evaluate uncertainty of the model. So here just showing the DFT calculated green line, the density states projected onto the oxygen 2p states, and the blue is the model predictions. So for oxygen, we only consider one frontier orbital with oxygen 2p, designed 2p states. So for this simple model, we can really capture nicely the main features, including the bonding states and anti-bonding states for a broad range of the pure metal surfaces, and really nicely. So in terms of energy, so this is the DFT calculated oxygen binding energy on those metal surfaces, and this is the model prediction. We have about 0.1 EV Rubin square error. And for each metal, we can evaluate, because the parameter side we have from the Bayesian learning is distribution. So you can evaluate the standard deviation of the model prediction. So basically, this really nicely put the error bar on the model prediction to see how reliable of the model is compared to the DFT calculated absorption energies. So from here, basically we have a reasonable model to capture not only the structure but also the bonding properties for the oxygen on metal surfaces. We did the same thing for OH and OH, so we're not going to show them here. So we can learn a lot from the physical model. So sorry, this is the basic slides. So the question we are trying to answer basically is why the OH and OH are strongly correlated. So if you look at it, the left graph. So this is showing the OH adsorbed on these 5 metal surfaces. So the blue point represent the hybridization energies, including the interaction with the SK states and also the localized D states. So they roughly linearly correlated to the interatomic coupling metal element, basically how much the coupling of the adsorbate, this oxygen 2p states with the metal D state. And also for the poly repulsion, this shown on this red point, it also linearly correlated to this parameter. So we observe the same thing for OH. So basically, for both the repulsion energy and the hybridization energy, they are linearly correlated to this interatomic coupling metal element. That's why they are strongly correlated in nature. So we can learn a little more if it is possible to break scaling between these 2 different adsorbates. So the question basically trying to answer here is, for example, if we want to shift the d-band center of the platinum or any metal by a small amount, simply perturb it without changing all the other power moments of this distribution. So how does it affect the binding energy in terms of the oxygen and OH and the OH? So here we are using the OH and OH example shown here on the right. So for different metal surfaces, what we see here is so basically you move up and down the d-band center, even though you're not influencing all the other moments. The binding energy are still linearly correlated on this parity plot shown here. So that means if simply perturbing this d-band center of the metal site of D states, you're not going to break the linear correlation between OH and OH. So that's really give you some sort of fundamental understanding which parameter is really the parameter we can play with. But unfortunately, we did all the other moments, and I'm showing here them on the right. So we can perturb not only the center, we can try to perturb the width and skewness and kurtosis of the D-state distribution separately. And what we see here is, so this shows the sensitivity analysis of basically tell you how the absorption energy of different intermediates responds to the electronic structure perturbation. We can see here the 2 adsorbates almost have a similar sensitivity to D-state perturbation up to fourth moment. And above the fourth moment is really difficult to manipulate in catalytic design. So basically the question, the answer we're showing here is so basically it's difficult to break the scaling of the OH and OH by simply perturbing the metal D states distribution. And one interesting thing we see here is for OH and OH, it turned out the third moment playing a more important role than the lower moment. That's something we are trying to understand further to see if we can explain a little bit better in terms of how the influence these states and the chemical bond. So this is a conclusion slide, a quickly summary. So by learning from DFT calculated electronic structure and the absorption energies, you can develop some physical models with some uncertainty quantifications as shown on the right. And another thing, the benefit about physical model is you can infer some physical insights from the model, see how different factors and influencing the chemical bonding of different adsorbates, and to see it's really possible to break scaling by changing different electronic structure of the surface sites. And by using the OH example, what we see here is really difficult to break scaling between the 2 different adsorbates simply by a monofunctional site under Newns. So that suggests us maybe we have to go beyond this simple site tuning to library some multifunctional adsorption sites to possible to break scaling. So this I want to acknowledge the funding from NSF catalysis program, and my student Wen Wang and Mang and also Xin, they did all the work. And finally, I acknowledge the community resources from Virginia Tech. So hopefully I have some time to answer your questions.
All right, thank you very much, Hongliang. We've got a couple of questions. Unfortunately, in the interest of time, we'll be posting these questions to the Google Doc you all have access to, and we'll be forwarding those to Hongliang so you can provide a written answer.
Okay.
Thank you, Hongliang.